Swayam Prabha. Digital India. Educated India.
Okay, today we will be looking at programming the Puma Robot using VAL 2 language. So, Puma Robot was the earliest robot 1960s, which was made by the Unimation company. So, Puma stands for Primary Universal Machine for Assembly, and this robot was made for assembly. And the structure of the robot is essentially, it is almost similar to the human body, the arm. So, the first joint of the robot is what is called the waist. So, this is the teach pendant by which we can move the robot and also program the robot. So, this is the teach pendant which has the joints 1, 2, 3, 4, 5, 6 joints, and this is having toggle keys plus minus plus minus. So, if I move any of the toggle keys, then essentially this the robot is going to move. So, the first joint of the robot is the waist axis, which is similar to our waist. So, when I move my hand, we move across the waist. So, this is my waist axis, and my hand moves like this. So, this is my z axis about which I am rotating. The second axis is this one, which is called the shoulder. So, when my hand goes up and down is the shoulder axis. The third axis is the elbow axis, which is like this, which is called the elbow. And then at the wrist we have the roll axis, the pitch axis, and the yaw axis. Okay. So, we have 6 degrees of freedom, and similar to this we have exactly 6 degrees of freedom on the robot. So, the first axis is called the waist axis, which is similar to the human waist, and the direction of the axis is vertical, as you can see there. The second axis, let me turn it this side. So, this is my waist. The second axis is the shoulder. So, in the shoulder axis, the hand can move up and the hand can move down. Okay. So, this is called the shoulder axis, moving the hand up and down. The third axis, which is similar to our hand, is called the elbow axis, and this is my elbow axis, which is moving the arm up and down. The fourth axis is called the roll axis. So, that is my roll axis, which is rotating the wrist at the wrist. Okay. So, this is called the roll. The fifth axis is the pitch axis, which is putting up and down the end effector. So, this is my pitch axis, and the sixth axis is the yaw axis, which is in this case it is looking as a roll about the z axis. So, the last 3 axes, the fourth axis, which is the roll axis, the pitch axis, and the yaw axis, they are intersecting at a point, and this is required for having an inverse kinematic solution. So, we can program this robot by using the teach pendant, which is shown here, or we can write a program. Now, in our earlier classes about VAL language programming, we have seen that the basic commands which are used in VAL are moves to move the robot arm from one point to another point. So, the first thing that we have to do is to define a point in space, and we define points in space by assigning the variable name, say point P1, and giving a coordinate. Then we say move P1 or move P2, and for the gripper we have open close commands. So, the essential commands that we are using in VAL are point, move or moves, open close, and approach and depart. This was covered when we talked about VAL language programming. So, what we will do today is we will write a very simple program for this robot. So, suppose the robot is in one end. So, let us move the robot to one end here to one side, okay, and say that this is my point P1. So, what I am doing is, suppose there is an object on this table. Suppose I want to pick up this object on the table, okay, and this is the robot, and if you can imagine the robot to be same as my hand. So, I say that my hand is here and this point is P1. So, this is equivalent to the point P1 there. Okay. So, then if I want to pick this up, what I do from P1, I will come to the point P2, which is very near or just on top of the object, and from here P1 I come to P2. Then this is my P3 point. I will go down and catch this object, take it up to P2, take it to P4, some other point, and then drop it and come. Okay. So, what we are basically going to write a very simple program. The hand is somewhere called a point P1, then I will come to a point P2, then from P2 I will open my gripper, I will go down, I will approach the object and keep a distance of 150 from the object. Then I will go down and catch the object, okay, and then after catching the object I will depart. So, it will come up again, okay, and after coming up to this point P2 again, it will go to the point P4 and then maybe drop the object and then come back to P1. So the program would essentially mean coming from P1 to P2, opening the gripper, going to P3, coming back to P2, going to P4, opening the gripper, and then going back to P1. So I will basically write down or draw the sequence here. So we are at a point P1. Let's call this point P1. So the robot is at a point P1 now, and there is some object here which I want to catch. Let's say there is an object kept on a table that I want to catch. This is my point P3. Okay. So the program we will write would be that from point P1 it will come to point P2. This is my point P2. Then it will open the gripper, and after opening the gripper it will go down, okay, and come and wait to the point which is just about 150 on top of P3. Then it will come to P3, close the gripper, and then go upward again to P2. Then from P2 it will go to P4, some other point, open the gripper, drop the part, and then it will go back to P1. So this is the sequence for which I am going to write the program using VAL language. So point P1, it will go to point P2. So you can look at the program here, which I have written very. So first is edit demo 1 means the name of the program is demo.1. That's the name of the program. Then move P1. So the robot could be somewhere else. So before it starts the operation, it should move to point P1. So the first line is move P1. P1 is the point which we have to define. We'll see how. Next is it moves to point P2. So it moves to the point P2. Okay. Then it has to approach the point P3. So we have seen when we studied VAL language that we don't directly go to the point P3, but we come somewhere on top of the point P3 and wait there using the approach command. So the approach command will ensure that it will come here and it will stand at a distance of 150 on top of the object. Okay. Okay. And then we are going to open the gripper, which is open eye. After opening the gripper, it will go down to P3. So moves. So please note that this is move and this one is moves. So it will move in a straight line and go to the point P3. Then it will close the gripper, and then it will depart, means it is departing. It is going straight up by a distance of 150. Okay. And then it moves to P4. So from here it will move to P4. So from here, so this is my point P4, and from here it will move to P4. So this is the point where it departs, and then from here it will go to P4. Now after going to P4, so move P4, it goes to the point P4, and from P4 it will come back to the point P1. Okay. Sorry, in P4 it will open eye, drop the part, and then it will come to the point P1 here. So we can keep repeating the cycle a number of times. Okay. So the basic program, as you can see, consists of the move commands, which means move to this point. Then it is approach. We said that when we are catching an object, we don't exactly go to the object, but we come somewhere on top of the object and wait with approach, open the gripper, and then go down straight. Okay. And that is done because to ensure that always the catch motion is straight and the depart motion is straight. Okay. So we are using the approach command here and the depart command here. So the basic commands are move, approach, open, close, depart, and that's it. So using this, we can write the program to perform this cycle, where the robot from one point will go to another point, catch the object, pick it up, go somewhere else, drop it, and then go to the third point. So I'll write the program very quickly. I'll type in the program in the so this is the monitor, and this is the keyboard, where this is using basic-like structure, basic-like commands. So I'll type in this in the command, and then I will execute it. So exactly this program I'm going to type in. So edit. So edit demo.1 is the name of the program. Okay. So the first command is move P1. Okay, let's use some other name. Let's call it some other name. So demo.1 is already there. So let's say demo.5. Okay, so demo.1 is already here. So I'll just change the number to demo edit demo.5. So that's a new program. Okay, so it says program demo.5. Okay, so that's the name of the program. So the first line I will type exactly this command in that sequence. So it is move P1, that is move to the point P1. Then we say move P2. Then we say approach the point P3 and keep a distance of 150. Okay, and then we say open open I, which means open immediate, then moves P3, that is the point where the object is kept, and then we come to close I, and then it is departs 150. So after catching the object, it will depart, go back straight 150, which is here. So it goes back to this point, and then from this point we want it to go and drop it at some other point. So P4. So we say move P4. So it has moved to point P4. So after moving to point P4, it is opening the gripper and dropping. So we say open open I, and after that it moves back to the start point. So from here it moves back to the start point P1. So we say move P1. Okay, so we have entered exactly these commands in the monitor by using the keyboard. Okay. So now next what we need to do is, we have written move P1 or move P2, but it doesn't know what is the points P1, P2, so we have to teach it the points P1 and P2. Okay. So I will start off by teaching it the points, the P1 and P2. So for teaching the points, I can use the teach pendant. So using the teach pendant, I toggle the joints and I say that is my point P1. Okay. Suppose that is the point P1, that is this point, okay, in space now. So now what we will see is, we will say here is the point P1. Okay. So the command that we use here is called here P1. So with this it understands that this point is actually P1. So now when I say right here P1, it will actually show me the coordinates of the point P1 in space now. Okay. So you can see that it has 6 parameters, the x, y, z, and the theta 1, theta 2, theta 3 at the end effector. So the x coordinate is 663, the y is -78, z is 427. This is in millimeters. So the base coordinate of the robot is 0, 0, 0, which is at the base there at the waist of the robot, and this is the x, y, z, and theta 1, theta 2, theta 3 are at the wrist. So now if it is saying that do you want to change this, so I say yes. So now it has assigned this coordinate to the point P1. Okay. So we have taught it the point P1. So next I want to teach it the point P2. So what I do is I move this here, let's say. Okay. So I move it here, and this comes down a little bit more. Okay. So this is my point P2. So I will teach it again and say this is here P2. Okay. So again it is giving me the coordinates of that point. If I am happy with the coordinates of the point, I will enter, and it understands that this is the point P2 that I want. So I enter here. Now I have taught it the point P2. Okay. So that is the point P2. Now I want to teach it the point P3, which is let's say a little bit down. So I bring it down. So I bring it down here and say that is the point P3. So this is the point P3 where I want to pick up something from. So I will teach it the point P3 as that point. Okay, so that was my P3 point. So I will say here P3, and that is the point. It is also giving me the coordinates of the point P3. Okay. Now I have taught it the points P1, P2, P3. I have to teach it the point P4 now. So that is maybe that side. So I move the robot that side where I want to go and drop it, and so maybe it has to go and drop it at some other point that side. Okay. So that is my point P4. Okay. So again I will teach it the point P4 and say here is P4. Okay. So it understands that this is the point P4. So I have taught it P1, P2, P3, and P4. Okay. So now I have taught the various points P1, P2, P3, and P4, and I am going to execute the program now. Okay. So the program, before executing the program, we have to set the speed. So speed command is speed. So we have to say speed, and if you are operating at say slow speed, it is at 20%. This is a percentage. So if it's a small speed, we are saying it's so full speed is 100%, lower speed is 10% or 20%. So let's say we are putting speed as 20. Okay. So after putting the speed as 20, I will execute the program. So, executing the program has the command of execute. So, execute demo .5. Okay. So, this command essentially the robot understands that I want to execute this program, and the program name is demo.5. Okay. So, I am going to execute the program. Now, when we are executing the program, okay. So, you can see that we are starting with point P1. So, this was the point P1 that I taught it. Okay. So, it is coming to the point P1, then it is going to the point P2. You can see exactly this sequence it is following. Then is going down, approach, and stopping. Okay. So, the exact sequence of operations that it was doing is it was going from P1. We will see that again. So, this is the exact sequence of operations it was following. That was my point P1. Then it went to point P2, that was somewhere there. Now, before it went to point P3, we are using approach. So, it is approaching the point P3 and waiting at a distance of 150. So, it was just coming down and waiting at 150. Then it is going down straight, because there is a straight line command which is move S P3. So, it is coming down, and then it is going backward again, which is after close I, it is departing 150, and then it is going to P4 and then coming back to P1. So, this is the cycle in which we are operating. So, this is an example of how to write a very simple program. Now, the gripper is pneumatic. At the moment, the pneumatic is not working. So, we are it is not opening and closing, but the open is open I and close is close I. Okay. So, if you are trying to catch an object, we have to open the gripper before we catch the object, and after positioning at the gripper, we have to close the object. So, this is for one cycle. If I increase the speed to 100%, okay. So, using speed command, I have increased the speed to 100%. Okay. So, I am going to make it 100% speed now. So, I will simply say 100. So, it is operating at full speed now, and so let us say speed. Okay. So, this is operating at a higher speed, but it is following the same sequence of operations that you can see. Okay. Now, a robot is not used for only one cycle or two cycles. A robot would be used for performing very large number of cycles, maybe millions of cycles. So, for that, what we can do is we can say execute here demo.5, and we can write how many number of times it should execute. For example, if I want it to execute 10 times, then I will simply write the number of cycles I want it to execute. So, the command is execute demo. This is the program name, comma, and this is the number of cycles that it has to operate. So, let us write it here as execute So, we are saying execute the program demo.5 10 times. Okay. So, the command is execute demo.5 is the program name, and 10 times is the number of cycles. So, we are looking at, so this is operating the same cycle, but it will be doing the cycle 10 times. Okay. So, in industrial applications, normally the robot will not be operating only once, but it will be operating for a very large number of cycles. So, it has a counter, and it is also saying that program has been completed and it has executed 10 number of times. So, there is a counter which keeps counting each cycle, and the moment it has reached 10 cycles, it will stop. Okay. But the sequence of operations was exactly the same. So, we can write very simple programs using val2 language like this, using very simple commands like move, approach, open, close, and execute pick and place applications, spot welding, spray painting, different applications. Now, in the earlier lectures on Val2 programming, we had talked about two commands. The first one was the difference between the two commands move and moves. So, there is a command move and there is another command moves and moves. Okay. So, this one basically takes the robot from one point. So, if I have a robot like this, okay. So, this is let us say move P1 or let us say move P2. This is my point P2, this is my point P1. Okay. So, if I say move P1, what it will do is, as there are different degrees of freedom here, so there are theta 1, theta 2 up to theta 6. So, what it will do is to go from here to here, it will find the minimum energy trajectory. Now, the minimum energy trajectory will not be a straight line. So, when it is moving from here to here, it will not take a straight line, but will take some other curved path in space, okay, but not a straight line. Whereas, if I use the moves command, then what it basically means, suppose I say moves P2, then what it basically will do means it has to follow a straight line and come from P1 to P2. Now, following a straight line takes more energy. Okay. So, unless it is required, this is not used. So, this command is not used unless when required. So, if it is just moving, we say move, but when we want it to follow a straight line, when it is picking up an object or dropping an object, then we are using the command moves. So, let us look at these two examples. So, that is my point P1. Let me take it somewhere else. So, this is my point P1. I have already taught it P1. So, let me write a program which will take it from, this program is essentially to show the difference between the two commands move and moves. So, we have move P1, let us call it edit demo.6, that is the name of the program, move P1, and then we say move P2, okay. And so, suppose I am here, this is my point P1, this is my point P2 in space somewhere, okay. So, I am saying move, so what it will do is it will take some other trajectory, and then I say move as P1, okay. So, from here to here it is going by following the command move. So, it is not taking a straight line, but taking some other trajectory, minimum energy trajectory. Then I am saying moves P1, so it is coming from here to here, and it is now in this case it is going to follow a straight line. So, we want to see the difference between this and this. So, let us write this program and see how it behaves in space. So, this is to understand. So, this is the point P1. So, let me teach it another point. So, let me teach it some other point P2. So, P1 is already known, right. So, that is my point. So, let us say that is my point. So, that is my point P2. So, what I do is let me write this program. Okay. So, here I am going to write a program again. So, edit demo.6. So, this is another program called demo.6. So, essentially this program says move to the point P1, move P1, okay. Then I am going to say move to the point P2. So, it has moved to the point P2. So, I am at P1, I am saying move to the point P2, and after it has gone to the point P2 taking a curved path, I am saying move in a straight line back to the point P1. So, now I am saying moves P2, okay. So, this is a very simple program to move between 2 points. Once it is going to move in a curve, and then it is going to move back in a straight line. So, that point let us teach it as P4. So, that is my P2. So, this is my point P2. So, I teach the point P1 is already learnt, P2 is the point which I am teaching it now. So, let us cut down the speed to 20%, then execute. So, first wherever the robot was, it is coming to the point P1. Right. So, it has come to P1. Now, you can see that it is going in a curve. If you can see that it has gone from P1 to P2 in a curve, but it is not being able to come back in a straight line. So that error is coming. So now let's change the coordinate a little bit, and so let me bring it there itself. And teach this as point P2. So here edit demo.6. Okay, so let's try to move it down a little bit. So this is my point P2. Let's move it to some other point. It is not being able to find the trajectory which is coming back this way. So it is going to come back using a straight line only. Okay, so this is basically showing how the robot can move from one point to another point. Let us bring it here. And say this is my point 3. So let's teach this as point 3. So now what I'm saying is P1 is here, P2 is here, and I define another point which is P3 here. Okay, so let's try P3. So what I will do is we will say move to P3 by using the move command, and then it will go back using the moves command. Okay, so these are two different commands to go from P1 to P3. So let's have a look at that. Okay. So what we have done here is we have written a program to take it from P1 to P2, then move, and then it moves in a straight line. Okay. So let me write the program again. So it is going starting from move P1, then it moves to P2, and then it moves to P3. P3 is another point, let's call it P3, and then it moves back to P1. Okay. So we have 3 points. We have P1 here, so it's my P1. This is another point P2. This is the point P3. Okay. So it goes from here to here, then it goes there. Now from here to here, we are using the straight line command, so it should move in a straight line. Okay. I basically want to show the difference that from here to here is going in a curve, then here is going in a straight line, and when it is coming back from here to here, it is again going in a curve. Okay. So I basically want to show the difference between the command moves and moves. So P1, P2, P3 is taught, so we have to teach it the point. If that's my point P3 here, P3. So I've taught it the 3 points, P1, P2, and P3. Okay. So P1 was already taught. It is somewhere on top. So, this is my point P2. Okay. So, let us say that is my point P2, here P2, and my point P3 is somewhere here. Okay. So, that is my point P3. Sorry, this is my point P1. So, from P1 it is going to the point P2, then is going to the point P3. You can see that it is moving very slowly because it is going in a straight line, and then P3 is going back in a curve. So, this is essentially to show that when we are using the command moves, the robot actually moves in a straight line and it becomes very, very slow. And the speed, it becomes very slow here because it has to compute that straight line path and then go in that speed. So, if I increase the speed to 100%, okay, and then if I cycle it, let us say 5 times. Okay. So, I have increased the speed and I am also executing the cycle 5 times. Okay. So, basically to observe that when it is going from here to here, it is going at high speed, but when it is using the moves command, okay, so when it is moving to the point P3, it is going very, very slowly because it has to go in a straight line. And then from P1, so from P3 to P1 again, it is going very fast. So, this is essentially to show, so if you see the motion, the curve motion is very fast, but the straight line motion is very slow. That is essentially because it has to do more computation. The inverse kinematics is more difficult. So, the moves command is only used for when you have to pick up an object and you have to go in a straight line, not otherwise. So, this is essentially to show how a very simple VAL2 program can be done using robot program can be done using VAL2 language. So, after this we will be looking at, we had studied about microcontrollers, that is the Arduino, and the using this microcontrollers we can make very simple. This is an industrial robot arm, so we can make this in a lab, and it has a very sophisticated controllers and actuators, and is also very, very expensive. But we can make very simple robots using very simple microcontrollers, tooling systems using servo motors, okay, which are very, very cheap, and by using the Atmega microcontrollers. Okay. So, after this we will look at another 2 programs where we can make very simple robots just to understand forward kinematics, inverse kinematics of 2-link system and also for 3-link system. So, 3 degree of freedom or 2 degree of freedom can be made very, very simple. So, let us move on and look at the next 2 robots which we can make in the labs by ourselves. Okay. So, after looking at the Puma programming, which is an industrial robot, we will look at very simple arms, how to make very simple arms using 2-link or 3-link systems and using microcontrollers, which you can make in the labs itself. Okay. So, first we will start off with a 2-link arm, and this I will explain the forward kinematics and the inverse kinematics of a 2-link arm, 2 degree of freedom, and then we will look at the forward kinematics, inverse kinematics of a 3-link system, 3 degrees of freedom, and then we will look at the actual robot, how to control it using a very simple microcontroller. So, we have 2 links which are which can be written like this. So, this is one link here and there is another link there, and this is my x axis and this is my y axis. So, this is my x axis and this is my y axis. This has been done earlier in class. So, I will go through it very quickly. So, this is my coordinate x y, and this x y can be written in terms of theta 1 and theta 2. So, this is my x 2. So, x is equal to L 1 cos theta 1 plus L 2 cos theta 1 plus theta 2, and y is equal to L 1 sin 1 plus L 2 sin theta 1 plus theta 2. Okay. So, this was explained in class earlier. So, the x and y coordinate here can be written in terms of theta 1 and theta 2 this way. So, this is cos theta 1 and this is cos theta 1 plus theta 2. So, this is my angle theta 1, that is my angle theta 2, right. So, when we solve it, we can write the solution straight in terms of this has been solved earlier. So, I will simply write the solution is equal to a tan, so a tan 2 and sin 2 cos 2, this is to find the angle theta 2, and the angle theta 1 can be written as, so angle theta 1 can be written as tan inverse of y L 1 plus L 2 cos 2 divided by minus x of L2 sin 2 divided by x L1 plus L2 cos 2 plus y L2 sin 2. Okay. So, this two link system has 2 degrees of freedom theta 1 and theta 2, and we can find the inverse kinematic solution for theta 1 and theta 2 like this. Now, what we are going to do is we are going to connect a servo motor, a small servo motor onto each of the joints, okay, and each of these joints will be connected to a servo motor, and this motor will be controlled by a microcontroller. So, we are going to have a microcontroller here, a microcontroller which is indirectly going to be connected to the PC. Okay. So, this is a very simple experiment which you can do very easily in the labs and very cheap. So, we can make 2 link system, connect servo motors which are very cheap. We can buy them for 400, 500 rupees, connect with the microcontroller and then connect it to a PC, and where we can, in the PC we can write the code for the inverse kinematics solution theta 1 and theta 2. This is for the forward kinematics. So, this is my forward kinematic solution. So, if I am giving my input theta 1 and theta 2 here, I am going to get the output of x y. In the inverse kinematic solution, this is my inverse kinematics, where if I give my x y, I am going to get the output of theta 1 and theta 2. Okay. So, this is a very simple experiment which can be done in the labs. You can make it. We will see how to do that now, how to write the program. The second experiment we will look at is for a 3 link system. Now, for a 3 link system we have, so these are my 3 links. Okay. So, look at this carefully. So, x, so this is a 2 degree of freedom, this was 2 DOF, this one is 3 DOF, 3 degrees of freedom. So, in the 3 degrees of freedom system, this is my coordinate system that I am using. This is my x axis, this is my y axis, okay, and this is my z axis. Okay. Now, if you can imagine, if I draw it in terms of DH parameters, then this is one link, okay. This is one joint here, okay, and this is another joint. Okay. So, this is one joint, this is one axis, this is another axis, and this is another axis. So, this is my 3 degree of freedom system. Okay. So, this is a 2 degree of freedom system which has 2 links on a plane. Now, if you rotate this plane about this axis, then it becomes a 3 degree of freedom system, right. So, this is essentially extending one more degree of freedom by putting a rotation about this joint, which is translating it into this kind of a system which is 3 degree of freedom. But here we need to understand something, that this 2 behave like a 2 link system. So, it is planar, which is rotating about this axis. Okay. So, based on that we will try and solve it using geometry, which is very simple to understand. So, this is one link, okay, this is 1 degree of freedom which is rotating about this axis, then there is another link here and there is another link here. Okay. So, this is my L1, this is my L2. So, the coordinate of this point here is x, y and z. It is 3 degrees of freedom. So, it has 3 coordinates. But now, if you look at the projection of this fellow, if you are projecting it down, what is the meaning of x, y and z? If you are projecting it down, it will come as a projection here, okay, if you can imagine, because this and this is a planar system. So, it is a plane actually. So, if I project it, it comes here. So, this is a projection on this is a projection on the x axis, and that is a projection on the y axis. That is the meaning of x, that is the meaning of y, and the top is the meaning of z. That is the meaning of the 3 coordinates x, y and z. So, we are going to use this solution and try and get this solution very simply. You can also use DH parameters and do inverse kinematics. This is just a geometrical solution. Now, if you look at the angles, this is my angle theta 1. So, this is my angle theta 1, this is my angle theta 2, and this is my angle theta 3. Okay. So, theta 1, theta 2, theta 3 are defined like this. So, the solution of this is the solution of these 2 are on this plane, which is same as this solution, and this solution is getting projected onto this. So, cos of this length is going to become my x coordinate, and the sine is going to become my y coordinate. Okay, that is the meaning of the 2 coordinates. Okay, so, we will look at the inverse kinematics of the 3 degree of freedom system now. In the 3 degree of freedom system, it is an extension of the 2 degree of freedom. 2 degree of freedom has these 2 links. So, we have the 2 links, and these 2 links are moving on a plane. So, this is my plane, and this plane is being rotated. So, essentially there are 3 angles theta 1, theta 2 and theta 3. And we are going to reduce this problem to this to try and solve it in terms of using geometry. So, what we can see is that the projection of this point is coming here. So, essentially this length is equal to this is behaving like a 2 link system. So, it is L1 cos theta 2 plus L1 plus L2 cos theta 1 theta 2 plus theta 3 is this point. So, we have our two equations which are, and the projection of this line is cos theta component here and sin theta component there. So, this line here is essentially L1 cos theta 2 plus L2 cos theta 1 plus theta 2. Okay, so, that is this line. Now, this line is getting projected onto this side as a x component and is getting projected onto that side as a sine component, right. So, that is becoming my x and my y. So, we can write these two equations as x is equal to L1 cos theta 2 plus L2 cos theta 1 plus theta 2 plus theta 3. So, this is L2 cos theta 2 plus theta 3, and it has a component this side which is a component of cos 2, sorry, cos 1. Okay, so, this has a component of cos 1. Now, y is equal to L1 cos 2 plus L2 cos 2 3 into sin 1. Okay, so, this line here is L1 cos 2 plus L2 cos 1 plus cos 2. So, this component here is my x coordinate and the component that side is my sin component. Now, and what is z? Z is equal to L1 sin 2 plus L2 sin 2 plus 3. So, I am writing it in short. So, 2 plus 3, right. So, that is my sine component. Okay. So, this is my, so what is z? Z is this component, that is z. So, which is equal to L2 cos 2 plus L2 cos 2 plus cos 2 plus cos 3, right. So, we are getting my x, y and z coordinates. Now, I can take, I can try and use this solution itself. So, I reduce it to this way into this equations, then I square and add and get this. So, what we will do here is we will reduce, I will simply bring the cos here and the sine here and then square and add. So, what we get is L1, so x by cos 1 is equal to L1 cos 2 plus L2 cos 2 3, and if I bring the sine here it becomes y into sine 1 is equal to L1 cos 2 plus L2 cos 2 3. Okay. Now, so I get one equation here from here and I get the other equation which is this one, and then I square and add. So, L1 sine 2. So, this is my z coordinates. So, L1 sine 2 plus L2 sine 2 3. This is what we get. Then we can square and add, and what we get is cos 3. Cos 3 is equal to x by cos 1, x by cos 1 squared plus z squared minus L1 squared minus L2 squared divided by twice L1 L2. Okay. And from here cos 3 I can find what is sin 3, I can find it in terms of 1 minus cos 3 squared, and then I can find 3 as a tan 2 sin 3 cos 3. Okay. And from here we can compute tan theta 2 as simply using geometry z into L1 plus L2 cos 3 minus x by cos 1 L2 sin 3 divided by x by cos L1 plus L2 cos 3 plus z times L2 sin 3. Okay. So, exactly similar structure of the answers come, and using this we can do the forward kinematics and the inverse kinematics. So, forward kinematics would mean putting our input is theta 1, theta 2, theta 3, theta 2 and theta 3, and I am going to get x, y, z, and inverse kinematics would mean that giving x, y, z, and I am getting my theta 1, theta 2 and theta 3. Okay. So, what we are going to do here is next we are going to put motors onto each of the joints, connect the motors to the microcontroller. The microcontroller will be connected to the PC, which will be having these equations in the forward direction and in the inverse direction. So, we can do the forward kinematics and the inverse kinematics solutions. Okay. So, let us look at the lab setup to look at how we can make this, how we can embed this into a microcontroller program and then run the system itself. Okay, so we have looked at the basic theory behind the forward kinematics and the inverse kinematics. Now, we will look at how to make a very simple robot and utilize all what we have looked at. So, this is a 2-link arm. So, these are 2 links. So, this is one link here you can see, and there is another link here. They are connected by servo motors, which are very small motors, which have a DC motor, a potentiometer, and a PID controller all embedded inside. So there is one motor here, another motor there. So it is a 2 degree of freedom system. So there is 1 degree of freedom here, another degree of freedom here. This one is a 3 degree of freedom system, where there is one motor here. So this is my one motor, which you can see here is the base, and there is a second motor here, the 2nd degree of freedom, and this is the third motor, which is 3rd degree of freedom. You can also add a gripper here, which has a 4th degree of freedom, but we are only considering x, y, z of this point. So it is 3 degrees of freedom. After that, we can add more here, but it does not matter as far as the coordinate of this point is considered. Okay, so this each of the servo motors are controlled by the microcontroller, which you can see here. So the microcontroller essentially drives the motors using pulse width modulation, and these are connected to a PC. So in the first program that you can see here on the screen, this is using library functions of my servo to drive the 2 motors. So it has my servo, you can see here theta 1 and theta 2. So whatever value we give input here to theta 1 and then to theta 2, it is simply going to drive the 2 motors and take it. So this is approximately the forward kinematics, where we are giving the input of the 2 thetas and the output, the link is going somewhere. So what we can do next is we are going to give 2, let's say 60 degrees and 60 degrees. And you can look at this manipulator. So this is the 0, 0 position. So theta 1 is 0, theta 2 is 0. It is at this position. This is my end effector here. So when I give 60 and 60, what happens is this link is moving to 60 degrees, you can see, and this fellow has also moved to 60 degrees, and it has come to this position here. So this is very showing the very basics of forward kinematics and inverse kinematics. Now if I change the angle, it will go back again. Maybe you can change it to 30, 30. So what we are doing is here we are just giving the angle input, and that my servo program, which is a library function, is essentially driving the motor to bring it to 30 and 30. So now this angle, you can see this is my x axis. So this angle is 30 degrees. This angle with respect to this is 30 degrees here. Okay, so this is my x axis. So with reference to this angle is 30, and if this is my reference 1, with respect to this is 30. So this is essentially to show how the microcontroller program works for driving the motors from to a particular angle. Now we want to also look at the forward kinematics and the inverse kinematics. Now for that we have written a GUI. Now in the GUI, the equations that I just explained in terms of theta 1 and theta 2 in terms of the xy coordinate and the solution for theta 1, theta 2 are written in that, and using that we have made a GUI, and in the GUI these programs are written. So there is a forward kinematics and an inverse kinematics in both of them. Okay. So in the forward kinematics equation, again you can have a look at the GUI here. So this is setting it to 0, 0 position. Okay. So this is the GUI. Now inside the GUI is a program, and in the program we have written our inverse kinematics and first the forward kinematics and then the inverse kinematics. So this is showing the forward kinematics and this is showing the inverse kinematics solutions. And input here we are giving the joint angles in the forward kinematics. Maybe you can give 30, 30. So what it does, it takes theta 1 equal to 30, theta 2 equal to 30, and then and drives the and the inverse kinematics will find out the coordinates of the end effector point. So this is giving us the end effector coordinates. So this is end effector x and end effector y. So this is giving us the forward if you give a solution, if you give an angle here, it will give you the inverse kinematic solution. Now in the second case, so this is for forward kinematics, the second one is for inverse kinematics. So in inverse kinematics, if you give it some xy coordinate here, it will compute the angles theta 1 and theta 2 and then go there. Okay. So let us give some point, maybe 1 and 1.5 or 1 and so we have given a coordinates there, x and y coordinates, and it is computing the x and y coordinates and then going to the point. Okay. So if you change the inverse, if the required coordinates, it will again compute backwards and then take the theta 1 and theta 2. Okay. So this is how basically forward kinematics and inverse kinematics works, and we can write a very simple program, design this kind of very simple manipulators to understand how it works. Now let's look at the 3 degree of freedom arm. So the 3 degree of freedom arm has 3 axes. The first axis is this one. So if you can see, it is the 2 degree of freedom arm. So this is my 2 degrees, 1 and 1. This is moving on a plane, which is this plane. Okay. So this is moving on this plane. Now this link and this link are moving on this plane. Okay. So this is on this plane, and this plane is moving across this axis. So that is how it is becoming 3 degrees of freedom. So the Puma robot also actually has 3 degrees of freedom up to here, and then 4, 5 and 6 are at the wrist. Okay. So all robot industrial manipulators also have this basic structure. So they have one base which is going to rotate like a waist. This is called the shoulder, this is my elbow, and roll pitch you are here. So if I do the inverse kinematics for x, y, z up to here, then it is possible to control the robot anywhere. So this is the 3 degree of freedom arm. Okay, so this has 3 degrees of freedom, and as you can see the GUI here, this has the forward kinematics and the inverse kinematics. In this case, there are 3 degrees of freedom, so theta 1, theta 2 and theta 3. So whatever angle we give, that will the microcontroller will drive it to that particular angle, and this will go and position itself. So let's give let's say, so this is my 0, 0, 0 position. So this is 0, 0 for the base frame, the first axis and the second axis. The fourth axis we are not moving here, we are just considering x, y, z, the coordinate point of the end effector here. So we can give 30 degrees, 30 degrees, 30 degrees. So what we can see is that it has moved 30 degrees here, and 30 degrees of this one and 30 degrees of this one. This is a little bit, so we can increase it to maybe 60, 60, 60. So now you can see that this is, it has moved, it was here, it has moved that side. So this was my 0 axis, it has moved this side, so that is 60 degrees of the first axis. The second axis is this one, so this was my 0, it has gone up like this, that is 60. The third axis is, this is my 0 for the third, so it has gone like this, which is 60 degrees. So there is 60, 60 and 60, and it has come to some point in space. So this is the forward kinematics, where I am giving the input as the angles theta 1, theta 2 and theta 3. Now in the inverse kinematics, we can give corresponding angle, we can give the coordinates, and it will compute the inverse kinematic solution. So this is my 0, 0, 0 position. So it will compute the corresponding angle and go there. So we can input some numbers there. So we have inputted the corresponding number here, and then you can find that it is finding the inverse kinematic solution and then going to the end effector position there. So this is essentially to show that very simple robots which can be made, 2-link systems, 3-link systems can be made, and they can be controlled very, very easily. Most of the programs are available online and they are open source. And we can understand forward kinematics and inverse kinematics for 2-link systems, extend to 3-link systems. Now you will see that the extension of the 3-link system of this robot, the structure is same as the Puma robot. In the Puma robot, only it has 3 degrees of freedom at the wrist, whereas the basic degrees of freedom here are the same. So if you understand the kinematics of this, we can also understand kinematics of all robotic systems, because they are extensions of this only. And we can very easily make them. These are very, very cheap. They can be made simply by bending aluminum sheets, connecting by servo motors, and then controlling using Arduino microcontrollers. So this basically gives us an idea of how to make very simple robots, whatever we have studied, and how to program them, and how to understand the whole concept of robotics better. Okay, thank you.